Mhm. Very good. Very good. Let us start. Some people asked for a bit more time with homework, so I will not speak about solutions today. We'll talk about them next class. Today we are going to continue with shortest path discussions. I did change the order a bit. I think conceptually it's easier to handle first the case of graphs with arbitrary weights that can be either positive or negative, and actually to understand exactly what's in which cases we can provide better algorithms for these case these cases. It's even better to start with graphs that have topological order. So we will switch to graphs that has a topological order on them and then move back to shortest path. So let us define what is a topological order. I'll assume that my graph is a directed graph. Edges, every edge is an arrow. It has a direction from one node to another node. And I think the best example that I can think of about examples of the types of graphs that I'm talking about are graphs that has some priorities. Each node is some task, maybe even computer task, and the edge tells me that W, the vertex W, needs some input, and this input uh, is coming from a different task B. That is, whatever I do, I have to finish B before I can start W. Similarly, this edge tells me you have to finish C before you can start performing A. This edge tells me you have to finish A, which in turn for this you need to finish C and B, but you have to finish A before you start X, and you have to finish W before you start X. So this will be the type of graphs that we are going to look at in the next 20 minutes, and we actually will make one more assumptions in it. If indeed it's priorities between jobs that one needs to be concluded before I can start the other one, it's likely to assume that I don't have cycles in this graph. What is a cycle? Remember, we are talking about directed graph. It will be a bit strange to tell me that before I start B, I have to finish A, and in turns, before I start C, I have to finish B. Before I start C, I have to finish B. But before I start A, I have to finish C. because now with which one do I start? I cannot start with A because I have to finish C beforehand. I cannot start B because I have to finish A before that, etc. So we are talking about DAGs. DAG, directed acyclic graph, and we hope that the input graph here will be a DAG, but the algorithm that I'm going to show you, Kuhn algorithm, will also tell you, you know what, something about your graph or your priorities doesn't make sense because there is a cycle. So if there is a cycle in this graph, the algorithm will tell me. If there is not a cycle, the algorithm should spit out a topological order of the vertices. I don't know if you covered it in 345 or not, so to be on the safe side, it's a very easy algorithm. I'll cover it up. A comment about topological order. There is another algorithm that you might have seen for finding topological order, which is using DFS numbers, depth first search numbering. For example, the CLRS does not contain Kuhn algorithm, their main textbook. Instead, it contains topological order as a result of DFS algorithm. Since I'm not talking about DFS in this course, we will cover Kuhn algorithm directly. I also think that conceptually it's much nicer, is much easier to understand. So, what is topological order? Essentially, I have one processor and I need my tasks to be at every specific moment. I can only take care of one task. And I don't want to switch between one task or another. Remember, every node here is one of the tasks that I have to accomplish. And I need to finish all of them, but I'm asking at which priority should I do it? Which will be the first, which will be the second, which will be the third? And of course, I cannot perform A before I'm finishing C. That's what the arrows tells me. So the labels, the way that I think about them, is just the number that gives you the order at which you need to accomplish these tasks, such that when you want to accomplish task 5, all the tasks that you need beforehand are already done. Have smaller number. Formally, topological order is a label between 1 and n that I give to each one of the vertices. One will be will have the label of 1, 2, 3, 4, 5, all the way up to n. The label is a unique number between 1 and n is a number of vertices. Unique in the sense that I don't have two vertices with the same number. And what is a criteria? What I need to this labeling to do is that if you have an edge, directed edge from U to V, remember, U needs to be executed before V can be executed, then the label of U must be smaller than the label of V. It doesn't have to be the label -1, but it has to be smaller. While this is called topological order, I didn't find any explanation. Doesn't have much similarity with topology as much as I know, but that's the name that that people use. So this is a topological order of the graph, these numbers that we are going to give to the vertices. And the Kuhn algorithm will help us find such a numbering, and we'll do it very efficiently. Obviously, if I'll try to assign topological order to this graph, it's pretty much hopeless, because any attempt, let's say if I'll give B the label of 1, then I need to give C the label of either 2 or 3. If I'll give it a label of 3, I don't have any label to give to 1, so let's give C the label 2, which give A is a label 3. Remember, the rule said that if you have an edge UV, it's an edge in your set of edges, then label of U must be smaller than label of V. So I said, but I'm already stuck, right? Because right now I have an edge that goes from A to B, while the label of A is larger than the label of B. So there is no hope to find topological order if it's not a DAG. It's not a directed acyclic graph. It's a graph that has a cycle. Okay, let's see how the algorithm goes. So for the algorithm, I need to know what is the in degree of each vertex. Definition, the in degree of a vertex with a set of edges, not necessarily all the edges of the graph, but with some set of edges, it will be the number of edges that enters V. Okay, I don't care how many edges are leaving V, I'm asking how many edges are entering V. So in this case, the in degree of V is 3 because there are 3 edges going into it. The in degree of X3 is of course 0. There are no edges that goes into X3. Any questions so far? Good. Everybody feel comfortable with the in degree? How many of you have seen a topological order before? Just write in the chat. Yes, no? Yes, 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 yes. Yes, 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 yes. Okay. Yes, thank you. There is one. Okay. We will cover it quite quickly, but there is at least one person that didn't see it. Fantastic. So let's do it. Spend just a minimum amount of time that guarantees that we all understand it. With which vertex should I start? Which vertex can get, in our case, a label of 1? I'll start. It of course must be a label with in degree equals 0. When I start my algorithm, let's have it on the board. But I have B and I have C. B and C and A, W and A, and there is Y also, and X, and it goes D, W2. Okay, so I need, what algorithm is doing is storing a set of all the nodes who has no in degree. That is in degree equals 0, which right now tells us that S, R, W is not there, its in degree is 1, A is not there, S right now is Y, B, and C. The 3 of them, I can start my process in any one of the 3 of them. I'll keep a counter CNT that tells me what is a next in degree that I'm going to give a vertex. As long as S is not empty, pick one of the vertices that has in degree equal 0. Let's take B. just a bit different than what we did in the previous slide, and give it the label of count. So its label in the topological order is 1. And now for each vertex v with an edge uv in the graph, that is all the edges that are leaving u is a node that I just picked over here. For all the edges that are leaving u, what do? I remove them here from the graph. Okay, so I'll yeah, that is, I assume that I just executed vertex 1, so A doesn't need to care about its dependency, and B doesn't need to care about its dependency. And notice that when I'm doing so, the in-degree of W and the in-degree of W and the in-degree of A are also becoming 0, so I put them in S. Okay, so S contains now Y, B is removed, C, W, and A. I pick one of them, give it in degree, giving the current value of the counter. It moved to 2. Remove the edge connecting it. And of course, the in degree of X has been decreased. It used to be 3, now it's only, it used to be 3, now it's only 2. Because my trigger of realizing that I need to put a vertex in S is that it's in degree becoming 0. So we have 1, 2, pick now a next vertex 3, why not? Remove it, remove the edge connecting it. My only option now, the only vertex with in degree 0 is C. So it will be 4, 5, and 6. Voila. Okay, now we know how to find topological order. And it took me quite a few years to realize how important it is to have a good algorithm for topological order, and how many problems in graphs that are otherwise quite hard and are hard as NP hard sometimes, hard as takes a lot of times but still polynomial sometimes. How life are simpler on one hand if you have scenarios that you can represent as DAGs, and on the other hand that DAGs are much more common than I originally thought. So I think the topological order is really, really important tool. Moving along. Running time, of course, we spend a constant per each edge, constant per each vertex. Altogether, this is the optimal time, right? Because I don't know, that's the optimal time because that's how much information the graph contains. I need to pay attention to every unit of information of the graph, and this is a number of units that I do have. Which of the graph representation data structures should I use if I want to do it? Right, we have two ways to represent graphs. One was adjacency matrix, one was adjacency list. If I'm shooting for this running time, tell me in the chat. If I'm shooting for this running time, which of the graph representation should I have? Adjacency matrix or adjacency list? Yeah, distance learning sucks because when I was teaching in Gould Simpson, I know 906. It has a kitchen next to it, and I used to make myself coffee, and I figure out how little energy it takes. So I was making for the rest of the class. It took tiny little bit of energy, but distance learning. So. No answers. I need to be able for this algorithm to say, hey, I'm paying attention to a vertex A, and I want to know who are its immediate neighbors. It's actually directed neighbors, but in particular, I want to know who are the friends or the followee of A. If I'm using the graph as adjacency matrix, then for the vertex A, there is a row in this matrix with zeros and ones, and only the ones are the specifying that there is a vertex which is a neighbor of the vertex A. Right, so I have to run through through the whole list and spend n time per vertex to find its neighbors. If I want to find the neighbors efficiently, it must be adjacency list. Okay, so if I would shoot for adjacency list, this will be my running time. What would be the running time had I been using adjacency matrix? Anybody? Correct. It's excellent point. It's v squared plus e. I mean, everything would have taken v squared plus e, which I want to spend a moment. What is larger? Is this v squared, is it smaller or larger than the number of edges? And the answer is, it's a trick question. The answer is depends. It depends on whether your graph makes sense or not. Here is a very interesting graph at which I only have a pair of vertices, but I have a lot of edges. E's can be arbitrarily large. I have no idea why I need such a graph, but this is an example that E is much larger than V squared. Now it's actually much larger than V squared, but for this I need a lot of parallel edges. Also, it's possible that I have loops in the graph, a vertex with an edge that connected to itself. Possibly it's good for some applications, not for any of the applications that we will discuss. In the applications that we will discuss, we will assume that between a pair of vertices there is at most one edge, which means that the number of edges that we might have would be n choose 2. This is a number of pairs of vertices. However, if the graph is directed, then there might be one edge going upward, one edge going downward. So it's 2 times n squared. It's still smaller. N is a number of vertices. So it is still smaller than n squared. So usually we'll just say v squared. And yeah, that's the correct time. Okay, let's talk about Bellman-Ford algorithm. As I said, I think that conceptually Bellman-Ford is much simpler than Dijkstra, so I will teach it first. Remind everybody what is a negative cycle. Negative cycle is a cycle in a directed graph where the sum of weights of edges is less than 0. And it, as I mentioned last time, it makes a question of what is a distance from u to v, the sum of weight of the edges along the path from u to v. It makes this calculation meaningless. It's just a question that doesn't have any a reasonable answer because I'm looking for a path whose sum of weights is as small as possible. But if I'll go to this vertex and make several loops around the cycle, I'm pushing the cost of the distance from U to V lower and lower. I can push it all the way down to minus infinity. So what I need from the algorithm is to give me reasonable answers if my graph doesn't have negative cycles. And if I did create a graph with negative cycle, I need the algorithm to tell me, the algorithm should say, don't ask me stupid questions. You have a negative cycle, so you better check out your sources. So Bellman-Ford algorithm, it's not crucial. You can actually run it also on undirected graph, but what is a distance? But somehow undirected graph and negative edges are a bit contradicting each other, because let's think about this graph with edge of U to V, and I ask you what is the distance from U to V. It's an undirected graph, so you can do our trick with a cycle as many times as you want. So you can run the algorithm as well on a graph with in a graph which is not directed, but to make the description a bit cleaner, let's assume that the graph is directed. If you really want to work on a graph with undirected graph, one way to do it is if I have an undirected edge from U to V, then replace it with two edges, one from U to V and one from V to U. There are different ways to handle it. Let's start. I want to find in this algorithm what is the distance from the source. We didn't have, I should have it specifically. We need to find the distance from one source. The name of the source is S, to every other vertex. And the distance of a graph is just the length of the shortest path that leads to this vertex. Here is S, here is some other vertex T, and if the weights are 10, minus 1, and 10, then the length of this path, delta from S to T, should be 10 minus 1 plus 10, 90. Delta, as we saw last class, delta will tell me what is the distance from S to T, what's the length of the shortest path from S to T. We start and the source, small s, is a unique vertex. We give this vertex a value of 0. D will be some array that we are going to use that will give some estimation of the length of the shortest path. To be precise, what D, this array D, is telling us is what is the length of the shortest path that we found so far. Again, what is the length DOV will tell you what is the length of, we'll see it's the length of some path from S to V that we found so far. I'm making it even. And as the algorithm progresses, our estimation about this path will be better and better. It will be closer and closer to what is the length of the shortest path. So we notice the difference. Some path versus length of the shortest path. Okay. So far I just start the algorithm. What do I know about other vertices? Don't be confused by the notation. For every other vertex V, which belongs to the set of vertices, excluding the S itself. Because S itself, where I start as a source, I'll give it. I know what's the length of the path from S to itself, 0. And for every other vertex, I didn't find any path to any other vertex, so my best estimation is that there is no such path. How do I tell the algorithm that there is no such path? It says DOV is infinity. Max int, max float, whatever you are using to denote infinity. That's how I initialize the algorithm. By the way, did you study Bellman-Ford as well? Anybody say yes? Yes. Everybody knows Bellman-Ford? Oh, cool. Okay, how many don't know Bellman-Ford? Oh, nice. And you also know the proof to the algorithm? Okay, it says no. Not so much. We got a few. Okay. So how about I'll proceed a bit faster, and if because it seems that there is a handful that did not cover it, I'll go a bit faster and just be very and just tell me to slow down if I'm missing it. Yeah, so excellent question. The pi array over here. So when I'm going to end up with a path that will tell me, for example, that from S to T, out of these 3 vertices, I might go through this vertex, through A or B or C, depending on the sum of weights of the edges. When the algorithm terminates, every vertex can tell the other vertex the whole list of the shortest path to it. But then every vertex need to store the shortest path to it that have n square information. But n information per vertex, n information altogether. I don't need so much. That's exactly where I'm using the cut and paste lemma. Because let's say that I found that the shortest path from I need a few other vertices around it, a few other vertices that enters A, but let's say that I discovered, just an application of the on the cut and paste lemma. Let's say that I discovered that the shortest path from S to T goes through A. And now I'll ask you, what is the shortest path to A out of all the info, all these other edges? And your answer, cut and paste lemma, would be, hey, the A is along the shortest path to T, and that's why if I'll just take the red path and remove the thing that I don't need, it will be also the shortest path to A. since had you have a different way to reach A that is cheaper than this red edge, then it would be even a shortest path to T. So what T will tell me if the shortest path is the red, what T will tell me who is its predecessor along the shortest path. Pi of T will be A, telling me that the shortest path to T goes through A. A is a predecessor. And then I'll go to A. When I want to reconstruct the whole path, I'll go to A and ask A what was before you. So pi of A will be S. And pi of S will be null, because it's already the beginning of the shortest path. So that's about the pi array. So every time that I think that I found a better path that reaches S or T, I'll also change pi as well. So what Bellman-Ford is doing is it is going brute force finding the shortest path. And remember this approach because I'm going to speak about algorithms for the bi-criteria shortest path. And bi-criteria shortest path is a really important, really useful problem that Bellman-Ford is really going to help us solve it. What is bi-criteria shortest path? You're building the internet. Every edge has, you are planning your route. Every road, ignore the internet. Every road that you might take from the source to the destination have the speed limit, or have the time that it takes to go through this edge, depending on the distance, depending on the path. So it has a time, but it also has the cost of this edge. That is, every edge has a time that it will take you to go through it, and has a cost that is associated with driving it. Maybe it's zero, maybe it's zero, maybe it's a toll road, and you have to pay something for it. And now, what would you like to do? You want to go from S to T along the shortest path, but also along the cheapest path. And usually, the faster you go, the more money they'll charge you for it. You can think about flights, you can think about the internet. So the question of what is the shortest path contradicts the question of what is the cheapest path. I can say I'm going budget, so I don't care about the time that it takes me to drive, I'll just look for the cheapest. Or you can say I'm very rich, I'll look for the fastest road. Or you can ask what I'm willing to pay for this drive, only $30. What is the fastest that I can afford within a budget of $30? And all these questions are way harder computationally than the single criteria shortest path, where we have only the time or only the cost. And actually, the bi-criteria shortest path is already NP hard. We'll get back to it. Okay, we initialized everything in this way. Pi of every vertex, I don't need it yet. And now what's going on is there is an inner loop that just tells me d of v is a distance, as far as I know, of some path that reaches to v. D of u is another path. I'm picking on some edge uv, and I'm asking, hey you, no, I just found some path from S to U, and an edge from U to V, and D of V is a cost that goes to V. Right now, let's say it's 100. D of U, let's say, is 30. D of U will be 30. And let's say that the cost of this edge is 10. And at this moment, U tells V, you know, you are my friend, you are my neighbor. If you are I know that the best path right now, as far as the algorithm knows, the best path that reaches V cost 100. However, if you first drive to U and then use the edge UV, it will only cost 30 plus 10, making it 40. Would you prefer it versus the other path that we know about that reaches V, whose cost is 100? And V will take the offer because 30 plus 10 is better than the 100. If the cost of this edge would be 200, then you will still make this offer to V, that is, to reach to V, the cost of 30 plus 200. However, V will prefer to stay with its previous cost, with the previous best cost that he knew. So this is the famous relaxation step at which we are asking if D of V, the current cost of V, is higher than the cost that it will take us to go to U and go via the edge from U to V, then update D of V. The update is always pushing it down, always making it cheaper. Only if D of V is larger than this term, then D of V will accept this new cost, D of U plus W UV. So I'll update in the first case that the cost was 10, then if the cost was 10, then I'll update D of V to be only 40. And by the way, here comes the pi into the game. Beforehand, the cost that reaches V was going through X, and that's why a pi of V used to be X. Right now, if the shortest path is going through U, then the predecessor of V along the best path that I found so far should be V itself. That is, pi of V right now is going to be U. So that's what happened in this command. And notice there is absolutely no word here about at which order I'm accessing the edges. Any order that you want. However, after you performed the initial loop once and finished going over each edge of E, the algorithm tells you go and do the same trick once again. And the algorithm will tell you once you're done, go and do it again. To be precise, the algorithm tells you do this inner loop n times, and the number of vertices many times. However, in the first part, it tells you do it only n minus 1, v minus 1 many times, this inner loop of passing through all the edges. And only then do it once more. But what we expect to happen if your graph is well designed, the last iteration should not change anything about the D of V. If you did succeed to perform relaxation in this very last iteration, D of V would be still larger than D of U plus W of V. It can only happen if your graph has negative cycles, and in this case, there is an error. Your question was meaningless to start with. So in graph without cycles, we expect that this check of relaxation in the last step will not change anything, that D of V will be equal or smaller than D of U plus W UV. Okay, so that's what the code of the algorithm is doing. And at the end, D of V will be equal, as we'll claim, to the distance in the graph from S to V. the time, there is no data structure. It's really fast for graphs that are not very large. It's really fast because you don't use any fancy data structures, any fancy tricks. All you're going is just performing it again and again, no ifs. However, the inner loop takes order E, the number of edges, order m, and you're executing it n minus 1 times, so it's order m times n, number of vertices times the number of edges. A quick example, since people mostly know this, what's going on. Let's keep the animation. Let's see one step of the animation. So right now I'm looking at all the cost D's that I have right now. I'm accessing the edge from a B to E. It's called D of B right now is minus 1. D of E right now is 1 after this example. So D of B would go down to be minus 1 as well. What did I say? D of E will be minus 1 plus 1, giving you 1 as well. So far I didn't discover any path to a D. At some point in the next iteration, remember, order that I access the edges is completely arbitrary. At some point in the next iteration, I'm accessing the edge from E to D. D of the distance to D just beforehand was infinity, and E, playing the rules of U, in the case UV in the slide before, U asking D, hey, if we'll go from the source to E, it will cost you already a 1, because that's D of E at the moment, and then to go from E to D will cost minus 3, making it all equals minus 2, and minus 2 is a cheaper. How did it become 1? Minus 2 is and minus 1. Who gave? Somebody gave E. I think that my idea of going through half the animation does not make sense. I think that. Okay, let's see the beginning. I'm accessing the first edge. This is infinity, this is infinity. Infinity is not smaller than infinity. Infinity is not smaller than infinity. Finally, I'm accessing one edge that leaves A. So I'm changing D of B to B from minus 1, because 0 plus minus 1 tells me that it's minus 1. Okay. Okay. Let's skip the animation. You have it in the slides. And theorem, if G of V contains no negative weight cycles, then after you run Bellman-Ford, D of V is actually the real distance. Remember, D of V is an array that we keep. Delta is what the graph says is the shortest path, and the algorithm says that they are equal. And I really like this proof. I think that it's very elegant, and it tells us a lot of things, including all kinds of ways to improve the algorithm. It's very constructive proof. So I want to tell you that after I want to convince you that this claim is true, and let's do it in the following way. Think about the path that leads from S to Vk, the shortest path that leads from S to Vk. I'm changing the labels of the names, just changing the names of the vertices along this path, but this is the optimal path. Okay, so I'll just give the vertices, give them new names. I'll call S V0. I'll call the next vertex along the shortest path V1, next is V2, and so on until the destination. And I'll call it VK, whatever K is, depending on how many edges I have along this path. And again, and listen carefully to the proof, because it's really the beginning of a lot of algorithms that are based on the proof itself. It's very constructive proof. So let's look at all these edges. These are the order of the edges along the shortest path. And what happened in the first iteration of the algorithm? So the first iteration of where I'm executing the inner loop of the algorithm, I'm accessing and performing relax operation on each and every edge of the graph, including the edge that goes from V0 to V1 at some point. So after I'm accessing the edge from V0 to V1, again, remember that's the optimal path, then I'm sure that D of V1 will be the correct value. So D of V1 will be the correct value, and we will have a lemma that would say D of V1 will actually be no larger than the correct value, the length of the shortest path, and D of V1 after one iteration cannot be smaller than the length of the shortest path, because it's always the length of a path. So D of V1 is the length of the shortest path. It might be also the length of it might be that V2 knows the shortest path to it. It might be the V3 knows, but I don't know about the rest. But I'm absolutely sure that since I'm accessing this edge once, D of V1 knows the distance to it. Now, what can I say about delta in general? What is the length of the shortest path to each one of the vertices? So for each one of the vertices, D from S to H1 of Vi is what? Delta from S to Vi is just delta from S to Vi minus 1, cut and paste lemma once again, plus the weight from Vi minus 1 to Vi. What do I mean? That if this is the optimal path from S to B, then what is delta from S to B is delta from S to A, because A is a predecessor of B along this path, plus the weight from A to B. Okay. So that's just what happens along this path. The distance to each vertex is the distance to the previous vertex plus the length of the edge connecting them. Next, D of V is the length of some path from S to V. Delta is the cost of the cheapest path. So delta is always small or equal than D. Okay, delta, the true path, is always small or equal than D, because you can check it out. D is the cost of some path. Delta is the cost of the shortest path. So yeah, that's what the previous slide says. So back to the correction of the algorithm. What happened after one pass of all the edges? Throughout this path, I checked the edge goes from V0 to V1, and because of these two lemmas, I'm sure that V1 knows the distance to it. What happened in the next iteration? I'm accessing each one of the edges, including the edge from V1 to V2. So what will be d of V2 after the second pass of the edges? It cannot be larger than the length of the shortest path. However, it cannot be smaller than the length of the shortest path. Shortest path is the cheapest, so d of V2 cannot be cheaper than it, but I'm also claiming that d cannot be more expensive than the length of the shortest path, because the length of the shortest path to V2 is what? The length of the shortest path to V1, which V1 knows already, plus the cost of this edge. So the relaxation operation guarantees that d of V2 will not be more than the sum of this edge plus this edge. So after the second pass, V2 knows the distance to it. After the third pass, V3 will know the distance to it, and so on, all the way up to Vk. Okay, so it's really elegant lemma. Tells us that's how the knowledge about the shortest path is diffusing from S to other vertices along optimal path. And what confused most students that I'm sending to look at this lemma and use it in other contexts is the relabeling of the vertices. So I highlight these names V0, V1, ... Vk, that's not the original name of the vertices. It's the name of the I just give every vertex a different name once I know what is the shortest path to a destination, to T. Then I look at the optimal shortest path, which obviously I don't know originally, and just for the sake of the proof, I assume that some oracle went down to earth and told me what is the shortest path, and I give the names to the vertices according to what the oracle told me. And all I say right now is that as the algorithm progresses, more and more vertices along this path knows the length of the shortest path to them. Now, there is a chance that after one path of all the edges, Vk already knows the length of the distance to it. I'll ask you a bit more in the homework to clarify it, but there is a chance that everything is already saddled, already stable after one pass. But definitely I don't need more than these many paths. Okay, so corollary, if d of v fails to convert after v minus 1 passes, why v minus 1? Well, look at any path in the graph. How many the graph has v edges, so the length of any path that doesn't contain cycle, of course, simple path, a path that doesn't contain cycles, the length of the shortest path to every vertex is v minus 1. 3 vertices, only 2 edges. But that's only for paths that don't have negative cycles. What happens if I do have a negative cycle, say one edge with cost of minus 3, then A will keep decreasing the length of A multiple times. So if you can perform any relax operation after V minus 1 iterations, or V minus 1 passes of the inner loop, then definitely you have a negative cycle, and the algorithm will tell you, yes, there is a negative cycle, go check out. Don't ask stupid questions. Okay, now, why did I want you to know DAG in this timing? Of course, because if it happens that my graph is also a DAG, then I can have a much faster algorithm. Correct? If the graph is a DAG, then then one pass of all the edges is enough. If the graph is a DAG, directed acyclic graph, then one pass of all the edges is enough. How come? Well, here is the algorithm. We first run Kuhn algorithm that will tell us that there is a topological order of the vertices. And when we are done with Kuhn algorithm, then we have the labels of all the vertices. And now notice, every shortest path that leads from a source to destination, what happens to the label when I'm going along the shortest path? And don't be confused, these numbers are the labels from Kuhn algorithm. There is nothing to do with the length of the edges. But if there is any path in the, if I'm looking for a path from S to B, and I'm looking at the labels of the vertices, each one of them has a label, and what am I sure about these labels? That the label must go up. So maybe that's 3, that will be 5, that will be 7. I'm not sure that they jump by 1, but I'm sure that they must increase as I'm walking along the shortest path from any vertex to any other vertex. And that's really cool, because let's repeat the same path of the correctness of Bellman-Ford. However, I'll perform only one pass of Bellman-Ford, and I'll do it in which order of the vertices. Which order should I ask the edges, the vertices? I'll do it based on the labeling that I got from the topological sort. Is it too confusing? There is an order of vertices that the topological sort dictates for me. I'm sure that this order also respects the order of any shortest path that would be. The shortest path contains many other vertices and edges, but the labels must going up because the edges are directed. So if I'm running Bellman-Ford, Bellman-Ford told you, you are free to pick any order of the edges that you want. However, if it is a DAG, then we will change Bellman-Ford. We will not access the vertices in any order that we want, but instead the rule of U, the vertex that we pick to be U at each iteration of the code at the algorithm, will be first vertex labeled 1, then vertex labeled 2, then vertex labeled 3, and so on. What does it mean? It means that if along the shortest path S knows its vertex, it has a small label, and it knows the distance to it, that is d of S equals delta of S to itself. And now S, because we are accessing the vertices in the correct order, we are accessing the relaxation of this edge when S knows the distance to it. That is, after S knows the distance to it. So after we perform the relax operation, d of A is delta S A. That is, A also knows the length of the distance to it. Okay, and that is, I'm accessing this edge only after S knows the distance to it. I'm accessing, and I'll access the edge from A to B only after A knows the distance to it, because it has a smaller label than the label of B. So I know already the distance to it, and when I access the relaxation, again coming from the proof of Bellman-Ford, since it knows the distance to it, then d, after I execute this edge, d of B also equals to delta SB. That is, B knows the truth, the length of the shortest path, its estimation of the shortest path is correct. I mean, the whole reason that Bellman-Ford is not efficient is because I have no idea at which order should I access the edges. Had I know what is the optimal shortest path, I would then I don't need the algorithm, but at least this order is guarantees that the later edges of the shortest path will be accessed only after the first edges of the shortest path. In other words, all you need to do is only one pass of a Kuhn, well, you called Kuhn algorithm that runs in this time, and then one pass of Bellman-Ford that runs in this time as well. Right? It's only one pass instead of n patterns. Okay, so that's very cool. So that gives us that's the overall algorithm of shortest path, positive, negative edges, we don't care. In a DAG is only linear in the number of vertices plus edges. Okay, I guess what about Dijkstra? How many people do? How many people not? Say say no if you don't know Dijkstra algorithm. Not so fast. Well, should I assume that everybody knows Dijkstra algorithm? Okay. Perfect. Let's assume that everybody knows Dijkstra algorithm. Then let's start dynamic programming, our next topic. Okay, all the algorithms that we covered in the shortest path, including Dijkstra, I'll ask you a bit about Dijkstra and about the bichromatic shortest path, and about Bellman-Ford, I'll ask you. Eh, but these algorithms, including many others, are examples of dynamic programming. Let's see more examples of dynamic programming, and it will be much easier to tell you what is dynamic programming after actually we will see examples of of problems that are solved using dynamic programming. We can specify a few rules that hold for all the dynamic programming, which would be that sometimes problems that looks like they have optimal, that have exponential time, once we realized what the dynamic programming can work, we'll be able to give a much faster algorithms. And usually in all these problems, we can specify the problems in terms of some smaller subproblems, simple subproblems, and these simple subproblems depending on one to very few variables out there. For example, when I solve the distance from S to B, I used solution to the problem of what is the distance from S to A. I And the distance from S to A may be used the distance to vertices that are even closer to S. That's why Dijkstra and Bellman-Ford are examples of dynamic programming. A solution to big problems uses solution to smaller problems, and the number of smaller problems should not be too large. There should be only n or n square, n cube. We'll see an example with n cube running time of dynamic programming algorithm. And the first problem is that we'll discuss will be the Floyd algorithm for all pairs shortest path. Familiar? Not familiar? At this moment I'm a bit paranoid. People, anybody knows Floyd algorithm? Warshall-Floyd? Emmy and Jacob, where did you oh, wait. All these answers that I see are about a Floyd algorithm? Okay, at which class did you discuss it? Is it 345? 345. Okay, then we'll go to the next problem. Just more time for things that I find very cool. Anybody not, let's see, how many people don't know dynamic programming? Don't know, sorry, Floyd problem. None that is online at the moment, so we'll treat it as none. Just adjust the window. Okay, we'll survive. What about the longest common subsequence? Anybody knows longest common subsequence? LCS. The slides are all linked. I mean, I changed the order of the two shortest paths, but they are not linked. What, the dynamic programming or the shortest path? I'll make sure that the links are working, but you do know where to find them in the. You were able to access the previous slides, correct? Cole? Go to the course website, the Google Doc. The links are quite different just because I switched the order. Okay, I'll make sure I just switch the order. I started from Bellman-Ford and switched, but okay. Yeah, let's do LCS. LCS is cool, and I'm quite impressed from what you've covered in 345, but I'm aware that you didn't all study 345 with the same instructor, so I'm expecting different answers. How much time do we have? Yeah, LCS. We have time to define the question, the problem, and it will take just 2 minutes. We have one sequence X full of characters. Let's say A, B, C, B, D, A, B, etc. Y, a sequence of characters as well. That's another sequence. I want to find a set of, I'll put both sequence horizontally and you need to watch me now. I'm putting both sequence horizontally, and I can put segments that will connect one character of X to another character of Y, one character of X to another character of Y. The rules is that you're only allowed to connect B to B or A to A or C to C. That is, I can connect this A to either this A or to this A. So that's one rule, is that only the same characters are connected. And the second rule, that's the salute, these segments are not allowed to cross each other. You cannot have two segments that are crossing each other. And on top of it, one character is connect only to one other character. In this aspect, it's a matching. I cannot connect this A to two A's from the other side. And finally, I want to put the maximum number of such characters. And the LCS problem would be exactly how do I find such a sequence of segments that in turn corresponds to a sequence of A and a subsequence of X and subsequence of Y. How can I find it, and quite efficiently? And it's important problem because it tells you I worked on a file and you worked on the same file at the same time, and we just have two different versions of the same program. What is common between what I did and what you did? So we can only pay attention to what is different, or how much are these two files similar. That's a diff operation, or the comparison operation that you have in many editors, or in Unix and Linux it will be just write diff between two files, and it will tell you exactly what is this longest common subsequence, LCS. Okay, hope that you got something from today despite the unorganization and the improvisation along the time, even if you knew Bellman-Ford before. There will be several questions on Bellman-Ford and a bit less than I planned, but there will be questions on Dijkstra coming up also in the next homeworks. Great. Thanks, everybody. And I'll make sure that the links are all alive.